Hello everyone, in this video I'm going to be talking about logic gates. Now logic gates are types of digital processors. And what they do is give different outputs depending on the input or inputs that they receive. So ultimately they process information and allow things to work. Now I've done another video on transistors. Now transistors can actually be combined to make logic gates. In fact, logic gates are really made up of components like transistors and resistors. So these are, as it says here, digital processors. They give a different output depending on the input that they receive. Now, before we talk about the different types of gates that we have, there's a NOT gate, an AND, and an OR gate. Before we talk about what they actually mean and what truth tables are, we're just going to talk about digital systems to begin with. Now, digital systems are classed as either being on or off. Now, every connection in a digital system is in one of only two states. So we'll just make a note of that. So for every connection, they're ultimately in one of two states. And that's either on or off, high or low, yes or no, or even numerically 1 or 0, and you can kind of see where this is going. So every connection, digital connection, is in one of two states. Now, in reality, when we're referring to, if we take, for example, this 1 and 0, a 1 ultimately refers to a high voltage. So 1 is referring to a high voltage, and a 0 refers to a low voltage. Now, if we were to give those specifics, the high voltage we're talking around something like 5 volts, 4 to 5 volts, and for a low voltage we're talking around 0 volts or close to 0. So that's just a little bit about digital systems either being on or off. And the reason why I mention that is because when we talk about inputs and outputs, it's particularly relevant because each type of logic gate has its own sort of set of rules for converting inputs to outputs. And these rules ultimately dictate what kind of input and output we have, and truth tables allow us to show these inputs and outputs. Now, the important thing to do is really list all the different combinations of input values that we have when we look at these logic gates. So if we just keep in mind for the moment that 1 is a high voltage, 0 is a low voltage, these inputs and outputs can be in this particular state, either a 1 or a 0, depending on whether it's a high voltage or low voltage output ultimately that we want. So let's talk about the different gates that we have. So the first gate that we're going to mention is the NOT gate. Now the NOT gate is sometimes called an inverter. So as the name suggests, it's almost like reversing, does the opposite of what you'd think it would. A NOT gate has only one input, and the input is either a 1 or a 0. So if we were to draw this, it would look like this in terms of a circuit symbol. So we'll put this in place. We've got the input here, the output here, and this is our NOT logic gate. And so the input is classed as either a 1 or a 0, so that goes back to our idea of being in one of two states, an on-off, high-low, yes, no, 1, 0. It's the form of digital processing that these logic gates work by. So if we were to, next to this diagram that I've just drawn, for a NOT gate, talk about the inputs and outputs in this kind of table. This is known as the truth table. It tells you all the possible combinations. If our input here was 0, because it's an inverter or a NOT gate, the output would come out as a 1. And equally, if our input is 1, our output comes out with a NOT gate as 0. So it inverts the input, if you like. So this logic gate is processing the information and inverting it with this logic gate, and it's read as either a 1 or a 0. So there we have an example of a gate that has a particular input and delivers a particular output based on that type of gate, the nature of the gate. So there's a NOT gate, but we do have two others. If I shrink the screen, we're just going to talk about the final two. So there's the NOT gate. Let's talk about the AND gate. Bit of an unusual name, but this gate, called the AND gate, looks a little bit like this. Now what's interesting about this is that it has two particular inputs and one output. So we'll label this input 1, this is input 2, here's our output, and this time, instead of being a NOT gate, this is an AND gate. Now AND gates usually have, they can have more, but usually have two inputs. So we'll just make a note of that. So usually two inputs to this type of gate. Now each input again can be a 0 or a 1. So we need to consider all the possible combinations that you can get for this. Now an AND gate only gives an output of 1 if both the first input and the second input are 1. So let's put that into a table and I can explain what I mean by that one. So if we use the truth table again, input and output, and we're going to refer to input 1 and 2 here. I perhaps could have called them A and B to make it a little bit easier, but hopefully it will still make sense. If our input at A was a 0, or at 1 rather was a 0, and at 2 was also a 0, then our output would be 0. If we had 0 and 1, then our output is also 0. If we had 1 and 0, so if our first input was of 1 value and our second input was a 0 value, that would also come with an output of 0. And it's only when our two inputs, so input 1 and 2, are both a 1, so a digital signal of 1, is our output 1. Not the same as a NOT gate that inverts it, where a 0 leads to a 1 and 1 leads to a 0. Here in an AND, we need input 1 and input 2. That's the easiest way to think of it. Input 1 and 2 to be a 1 for our output to be a 1. And let's consider a third potential gate. And this third gate I want to consider is a bit of an unusual one. This is our OR gate. Put this up here. So this is our OR gate. And the OR gate just needs one of the two inputs to be a 1 for the output to be a 1. So for the OR gate, again, we've got two inputs, but it just needs one input to be a 1. Whereas the AND gate needed both of them. So I might just add that for reference here. Go both inputs to be a 1, to get a 1 for an output. So let's go back to our OR gate, where we said just needs 1. And we'll draw again the circuit symbol. But this one, it's a bit of an unusual symbol here. This one looks a bit different. It's a bit more curved, almost like a crescent moon. This would be our input 1 again. This is our input 2. Once again, we've got our output but this is an OR gate. Now, as I said, what that means is that only one of the inputs needs to be a 1 for the output to be a 1. So if we were to draw the table of input and output, again we've got 4 possible combinations. So let's refer to input 1 and 2 here. So our 4 combinations, if both of these were 0, the output would be 1. If this was 0 and 1, then our output this time would be a 1. If this were 1, 0, then that would also be a 1, and 1, 1. If I just shrink the screen again just a bit. And we'll be able to see this. If our 2 inputs were a 1, then output would once again be a 1. So you can see really clearly there, if I highlight this in another particular colour. So just here, we've only got one of the 2 inputs leading to an output of 1, and here we've got one of the 2 inputs leading to a 1. On the AND gate, we needed both inputs here to lead to a 1. And we can see on the NOT gate, to get a 1, we needed a 0 on the input. So it's quite a lot of detail there. We've got the AND, the OR, and the NOT gate. The final part of the story are the NAND and NOR gates, which have the opposite output of the AND and the OR gates, if you like. So again, we'll shrink the screen just a final time. We'll refer to our final 2. So our final 2 gates are the NAND gate. So it's almost like a NOT and an AND, hence the name NAND. So it's quite unusual. So we've got a NOT gate and an AND gate. So it would do the same as the AND gate in that you only need, well, you need both inputs to be a 1. But because it's a combined with a NOT gate, it would give the opposite output. So if an AND gate would give an output of 0, a NAND gate would give a 1, and vice versa. So let's again draw the symbol and show how this works. So we have 2 inputs again. Here is the symbol for a NAND gate. So once again we've got input 1, input 2, and our output. This here is our NAND gate, and if we draw the truth table of inputs and output, so this time let's put in place again our input for 1 and 2. Remember, this is a NAND gate, so it combines NOT and AND as 2 gates. So if input 1 came out as a 0 and input 2 came out as a 0, then normally the output would come out as 0 if it was just an AND gate, because we need one of them to be a 1. So that would be 0, but because it's a NAND gate, because it has the NOT component to it, what would be a 0 this time is a 1. If this value here was a 0 and this was a 1, again, that would be a 0 normally, but it would also be a 1 this time because it's reversed because of the NOT element to it, the N in the gate, the NAND gate. Equally, if this were 1 and 0, this would come out as a 1. And this is the most interesting one. If the input were here a 1, and here a 1, so if the first 2 inputs coming into this logic gate were 1s, that would be enough for the AND gate to give an output of 1. But because of the NOT element to it, remember, we invert it. So this time the output would show as 0. And finally, the last gate to talk about is the NOR gate. So we've got, if we just number them, we've got the NOT gate, number 1, the AND gate, number 2, the OR gate, number 3, the NAND, number 4, and finally number 5, NOR gate. So NOT, OR, AND, NAND, and NOR are our 4 main gates. And let's talk about the NOR. So again, in the same way that it would invert an output because it's of the NOT element, this would, again, if we just draw this in place first of all, input 1, input 2, here we have our output, and we said this was a NOR, which means if we draw our truth table, if I just put in and out this time here and look at our combinations, so if input 1 and input 2, if our values were 0 and 0, you'd expect it to be a 0 again, but because of the NOR element, because of the NOT aspect to it, the output is 1. If this was 0 and 1, if our two inputs were 0 and 1, now that would be enough normally on an OR gate to get an output of 1, because an OR gate just needs one input to be a 1. So because we have this one here, normally that would come out as a 1. But because of the N, again, this part, it's reversed. So our output this time is 0. Equally, 1, 0 would give an output of 0, and 1, 1, that would normally give an output of 1, is reversed. So the output once again is 0. So you can see we only get our output of 1 in this top instance here. So it is quite complex, but if we work this through from the top, these logic gates, then it is possible to combine all of these. And in other videos that I do, I talk about examples of how you use these logic gates. And a good example is in a greenhouse. So how, for example, you can get a warning light to come on, for example, given different scenarios. So there is relevance to this, but obviously you need to just take your time and recap this video. So we've got the definition of logic gates at the top, types of digital processes that give different outputs depending on the input or inputs they receive. Every connection is one of two states, on, off, high, low, but we not normally talk about it as a 1 or a 0, 1 being a high voltage, 0 being in real life a low voltage. And then we've got 5 different gates to consider: a NOT gate or inverter that will swap the output, an AND gate where both inputs need to be a 1, an OR gate where just one of the inputs needs to be a 1 to get an output of 1, a NAND gate that combines the NOT and the AND, and a NOR gate which combines the NOT and the OR. Okay, hope all that helps.